Welcome back. Today we're going to be talking about small angles. So that means if I have an angle here, x, what happens when that angle gets really small and close to the x-axis there. So when we're talking about really small, I mean when x heads to 0. So we're going to talk about the limits. Especially, today we're going to talk about the limit as x approaches 0 of sine x on x. We can look at cos and tan as well, but this guy is going to be very useful and we actually need it to prove how to differentiate trig functions, which this is a lead into, okay? It's a bit of a minor topic. So, let's start with this really nice proof. What I'm going to do is go out here and make a triangle. Boom. That's 1, that's x. What's this side here? Opposite hypotenuse. Well, that's just sine x. Okay? And we know that because it's what's the y coordinate of the point P as well. Right, now I'm going to make a non-right angle triangle there. Now just bear with me while I set this up. I'm also going to make a sector. Okay, and remember these are ones as well. Yep. And now lastly, I'm going to make another right angle triangle, but this time it's going to be this big one. Now what's the height of that side there? Well, I could look at it. I'll just redraw that triangle here. I know that this bottom is 1. I know that this is x. I know that this is what, and I just get tan because I've got opposite and adjacent. So this side here is tan x. Alright, now the way we set this up, we're actually going to use something that's called the squeeze theorem, which we won't be needing for quite some time. But I'm going to say this triangle here, that's that blue guy, right, is less than the orange sector. And that in turn is less than the big green triangle. Fair enough? This blue guy is smaller than the orange guy, smaller than the green guy. Alright, what is the area of that blue triangle? It's got a base of 1 and a height of sine theta. So area equals half by base times height. Orange guy, to sector. What's the area of a sector is half r squared theta. Area equals half r squared theta using radians. Equals a half, r is 1 by 1 squared by, and guys, I've used x, sorry, I'll use x for all of them. Sine x is less than the green triangle, half base times height, is half by 1 again by the height, which is tan x. Alright, now I just do some algebraic trickery. I get rid of those halves, they all cancel, and I can say that sine x is less than x, which is less than sine x on cos x, because that's obviously tan x. Now I'm going to divide through by sine x. Okay, so I'm going to divide through by sine x, and I get 1 is less than x on sine x, which is less than 1 on cos x. Now I'm going to flip them. I'm going to take the reciprocals of each term. And what happens to my inequalities when I take the reciprocal? They get reversed. Okay, so I'm going to get 1 is greater than sine x on x, which is greater than cos x. Now, what I'm looking for is the limit. Okay, I'm saying, so the limit, let's move this up to there. I'm going to say the limit as x approaches 0 of 1 is greater than the limit as x approaches 0 of sine x on x, which is greater than the limit as x approaches 0 of cos x. Now, that's just 1. I don't know what this is. This is what I want. The limit as x approaches 0 of cos x, we could just look at the cos graph for that, couldn't we? And he goes like, oh, sorry, that's a bit, oh. But anyway, as I get closer and closer to 0, he gets closer and closer to 1. So this guy here is 1. Now, this is the squeeze theorem here. It's saying that if I'm the orange line, right? And I'm orange. I'm in the middle. Let's if I have a function here, orange, and then I have the green guy on the bottom, and then the blue guy on the top. Alright, what this is saying is that I have to be in between the blue and the green. What if the blue and the green are actually the same thing? What if they're 1? That means these lines will get closer and closer and closer, and it's actually going to be the same thing. So I know that this is 1, I know that this is 1, therefore this guy here of sine x on x is equal to 1. Okay, that's the big thing for today. Okay, I'll leave that there. Okay, so this is the big guy. I've also said over here that the limit as x approaches 0 of cos x equals 1. And that might come in handy as well. Okay, 2. 3, which I'm going to leave for you, doing the exact same way as before, is for tan. I'm going to say the limit as x approaches 0 of tan x on x is also equal to 1. Now I'm going to leave that one for you guys. Okay. That's about it really for that. We're going to use this one here in the middle. We're going to use that later when we prove how to differentiate the cos or trig functions. Okay, these ones here I'm just going to show graphically. We can also look at these graphically, okay? Great. Sin x on x, this guy here. Boom. Just seeing what that looks like is a nice function. Aha. As x gets closer and closer and closer to 0, sin x on x equals 1. Let's look at well, you know cos x. I don't have to put cos x up. Let's try tan x on x. I told you that was 1, and I've asked you to prove that. Ooh, okay. So I'll just get rid of that guy. As x gets closer and closer and closer to 0, tan x on x gets closer to 1. And cos x we know. Another way of saying this, let's move this over here. Another way of saying it is as x approaches 0, tan x approaches x. You see, all I've done there is multiplied up. And also here you could say, as x approaches 0, I'll just put a little comma in, sin x approaches x. Now this is just another way of looking at it. If I bring GeoGebra back in, I can see, well, look, I've got my x there. That's y equals x. Scales a little bit out. Boom. Sin x. See, as I get closer and closer to 0, they're kind of the same thing. That's all that's saying. because obviously the gradient of sine, we'll find out what the gradient of sine x there is, but they're quite similar, so that's just an easy visualization of that, okay? Also, same could be said for tan x. Boom. As I get closer and closer to 0, that tan x gets closer and closer to sine x. But that's another way of explaining it. Boom. Sine x on x goes to 1. There. And tan x, but let's not worry about the tan x. Sine x on x goes to 1. That's the big guide that we're going to be using in a proof. You're only going to see this, apart from the proof, they're going to ask, you might see a question like this. Evaluate the limit as x approaches 0 of sine 3x on x. I go, oh, I don't know what that is. So I'm going to, let's put a 3 there. Yep. Put a 3 there, put a 3 there, so it cancels. I know that this guy is equal to 1. Therefore, the whole thing equals 3. Okay, that's it. We'll come back later and we'll do differentiative of trig using this and another couple of other little tricks. But I encourage you to run through that proof again, okay? It's nice. Squeeze theorem, sandwich theorem. Lovely. Okay, ciao.